This laboratory is about velocity of propagation, and in particular the velocity of propagation or speed of signals associated with electronics. The concepts associated with the measurements are straightforward. Simply measure a signal twice with a known distance between the two signal measurements. The known distance divided by a measured time results in a velocity. In the case of sound measurements, two microphones will be used to convert the sound waves to electronic signals for measurement with an oscilloscope. I came across the idea for this speed of sound measurement when I was reviewing material from a company I have bought equipment from. The company is Picotech, which is a UK firm which builds PC-based data acquisition units. In their experiment section, you will find their speed of sound experiment. As you will observe, the experiment setup is straightforward. Two similar microphones are separated by a 1 meter distance. Measuring the time difference between similar points on the two waveforms provides the time measurement. The two signals will not be identical, but similar points like peaks or zero crossings in the data can provide reliable points in which to measure the time difference. Any sound can be used as the stimulus, but a quick sharp sound like a balloon bursting, which was used by Picotech, or a hand clap, which I used, is best. Because the signal does not repeat, a single sweep oscilloscope measurement is necessary to capture the signals for display and analysis. Once the signals are captured, time data from similar points can be indicated on the oscilloscope and downloaded to the computer. Scope screenshot images for use in your word processing program and signal versus time data for spreadsheet calculations should both be recorded. As the Picotech website material points out, the speed of sound is affected by other factors, most notably in air by the temperature and humidity. But in a typical lab, it will be around 350 meters per second, which is around 2.8 milliseconds to travel 1 meter. In the lab, we will use one setup and each student will record their own data, picking at least 2 points on the waveform to record data from. The first peak and first zero crossing will likely be the best points, but each response is different. Individual screenshot images and spreadsheets are required. Here is a short video of the lab operation. The scope is in single sweep mode as indicated by the yellow light under the single button in the top right hand corner of the scope. A hand clap to the side of microphone 1 away from microphone 2 triggers the scope indicated by the run button, which turns to red when triggered when the acquisition is completed. With the signal captured, the scope cursors can now be moved and the time data recorded and screenshots downloaded to the computer. In this second part of the laboratory, we will measure the speed of an electronic signal on a cable. Because the velocity of propagation of electronic signals is much greater than sound, more than 1,000,000 meters per second, we need to have a greater distance between signal measurements. Fortunately, this is easily accomplished by using a long cable. In our case, a 25-foot or 7.62 meter cable. A signal generator will provide the signal to be measured, with channel 1 on the oscilloscope measuring the signal which enters the cable, and channel 2 measuring the signal after it has traveled the 7.62 meters of the cable. A 50 ohm termination load is also used. As in the case of the sound test, any stimulus signal can be used, but a sine wave with an amplitude of 1 volt peak to peak is a typical test signal. Another reason to use a sinusoidal signal is because we will be measuring both the time delay and the phase shift represented by the cable. Digital engineers often think in terms of time delay, whereas analog or RF engineers think in terms of phase shift, so knowing both aspects is important. As shown, the setup is once again straightforward. Because we are using a repetitive sine wave, we can use the normal, not single sweep mode, and utilize the built-in time delay and phase shift measurements. Using averaging allows the scope to acquire many values, reducing the noise or jitter inherent in time delay or phase measurements. Begin your measurements with a 4 MHz sine wave and continue to 15 MHz and 1 MHz steps, completing the lab handout table. Save screenshot image data and spreadsheet data for 3 cases. For example, 4, 8, and 12 MHz, or 5, 10, and 15 MHz. Here is a short video of the lab operation. A 4 MHz sine wave travels down the transmission line, providing a signal at the beginning and end of the line. Scope measurements of frequency, time delay, channel 1 to 2, and phase shift, channel 1 to 2, are configured and averaging selected under the Acquire button. Recording the data to a table and downloading the screenshots to the computer complete the data collection for the laboratory.